So we've seen examples of how the solution set for a linear system can have 0, 1, or infinitely many solutions. And now we're going to prove the theorem that it's always like this. So the solution set of a linear system always has either 0, 1, or infinitely many solutions. Now, to prove this, like I said, we've seen that these options are possible, so we don't have to prove that. And it's clear that they're mutually exclusive. You can't have 0 solutions and 1 solution at the same time, for example. So we just need to prove that there are no other possibilities. Okay, so we'll show that as soon as you have 2 solutions, you have infinitely many solutions. So let's see. So suppose that x is a solution and that y is a solution for a linear system with coefficient matrix A and constant vector B. All right. And suppose that x and y are different. Okay. So let's see. Now let's consider a linear combination. We'll take z. And we'll take z to be a linear combination of x and y. And what it's going to be 1 minus t times x and t times y added together, where t is any real number that you like. Okay, and so let's actually call this z sub t, since it depends on t. Okay, we'll see that this z sub t is also a solution. So how do we do that? Well, we hit it with a and see what happens. So a times zt is a times, and then I'm going to take a copy of this, expression that I just wrote in the previous line and substitute it in there in the blue parentheses. So that's my zt. Now let's see what damage I can do to this with matrix arithmetic. Well, I can distribute the a across the sum. So it's a times 1 minus tx plus a times ty. Now here, t is a scalar, right? It's not a vector, it's just a scalar. So I can pull it out in front. And 1 minus t is a scalar as well. So I'll pull 1 minus t out in front. And I have ax. And then I have t times ay. And what can I do with this? Well, I started this story by making the assumption that ax is equal to b and ay is equal to b. So using those substitutions here, I have 1 minus t times b plus t times b. And if I count up the b's that I have here, then I have 1 of them minus t of them plus t of them, and those ones cancel. And so reading from the very most left to the very most right, I see that zt is also a solution. And it doesn't matter what t I chose. And since there's infinitely many t's, then there's infinitely many solutions. Okay, and that actually gives you a little bit more insight. So I'll give you a box because we finished the theorem. So there's the end of theorem marker. But it also tells you that, in fact, any point on the line that connects x and y is also a solution, because that's exactly what zt is. So zt is a point on the line through x and y. So if you had, you know, x over here and y over here, then zt is going to be some point on this line. If z is a number between 0 and 1, it's going to be here. Otherwise, if it's negative or greater than 1 or something, then it'll be out somewhere else on this line.